that unfolded in the distant past about 4.6 billion years ago, deep within a solar nebula. Nebulas, the cradles of stars, are where the very lights that fill our night sky come to life. These stars may seem like massive balls of fire, but inside them a delicate balance is at play. Gravity pulls inward while thermal pressure pushes outward. This balance, known as hydrostatic equilibrium, is what keeps stars stable throughout most of their life. But when this balance falters, stars transform, expanding into red giants or collapsing into white dwarfs, neutron stars, or even black holes. And all of this, the birth, life, and death of stars, is governed by just a handful of forces. For to be exact, beyond gravity and thermal pressure, there are the powerful strong nuclear force and the elusive weak nuclear force. Together, these forces shape everything in our universe. Every time scientists have uncovered a new force, it has reshaped civilization and redirected the course of humanity. Newton's revelation of gravity and motion set the stage for the rise of machines and fueled the Industrial Revolution. Then came Faraday and Maxwell, whose insights into electricity and magnetism not only lit up our cities but also powered motors and gave birth to instant communication via radio and television. Einstein, with his groundbreaking E=mc², unveiled the energy-fueling stars and cracked the enigma of nuclear forces. When Schrödinger, Heisenberg, and their peers cracked the code of quantum theory, they sparked the high-tech revolution, gifting us supercomputers, lasers, the internet, and the technology woven into our everyday life. Over the past century, physicists uncovered two fundamental traits shared by all forces. First, each force is carried by its own particle or bundle. Photons, for instance, transmit the electromagnetic force, while weak bosons and gluons handle the weak and strong forces. By 1984, these particles were thoroughly examined, though the existence of the gravity particle, the graviton, remains elusive to this day. Second, just as mass determines how gravity affects an object, particles have specific strong and weak charges that determine how they interact with the strong and weak forces. However, why these particles have the masses and charges they do remains a mystery. Einstein aimed to create a theory that would unify all the fundamental forces into a single framework, which he referred to as the unified field theory. He envisioned a concise equation that would enable him to, as he put it, understand the mind of God. But even the great Einstein could not make it. Scientists are now moving closer to a theory that could unify the four fundamental forces of nature into a single framework. This theory could potentially address some of the most profound mysteries in science, such as what occurred before the Big Bang, what triggered it in the first place, what exists beyond a black hole, and many such questions. The theory is now famously called the theory of everything. Today, I welcome you to join me on the enigmatic journey of the theory of everything. History. The night sky, with its dazzling stars, invites contemplation. It urges us to ask, is the universe governed by a higher plan? How do we find logic in its apparent chaos? Does life have a purpose? Or are we merely drifting in an aimless cosmos? The ancient Greeks were among the first to seek order in the chaos of the natural world. Philosophers like Aristotle theorized that everything was composed of four fundamental elements: earth, air, fire, and water. But how could such basic elements account for the complexity of the world around us? Over time, Greek thinkers offered profound ideas, such as the concept that everything is made up of invisible and indestructible atoms. They even believed that the diversity of nature could be understood through the mathematics of vibrations. Centuries later, Galileo Galilei emerged, challenging the established views of his time. He provided us with an improved telescope, allowing humanity to peer deeper into the vastness of space. Galileo's contributions to the scientific method, along with his work in the fields of motion and mechanics, would form the foundation for modern physics. His defense of the heliocentric model of the universe, though controversial, was revolutionary. Though Galileo died in despair in 1642, his legacy paved the way for future discoveries. That same year, across the English Channel, a child was born who would one day complete Galileo's work. His name was Sir Isaac Newton. He would unify the understanding of the cosmos by building upon both Galileo's and Johannes Kepler's ideas. Isaac Newton published his most famous work, Philosophiae Naturalis Principia Mathematica, in 1687. This groundbreaking book laid the foundation for classical mechanics and introduced Newton's laws of motion and the law of universal gravitation. With this book, the world came to know about one of the most profound fundamental forces of nature: the gravitational force. The force which is considered as the weakest among all, but when it takes charge, it gives rise to the most destructive object of the universe: the black holes. We experience this force every moment of every day. Newton's laws of motion had a key characteristic: uniformity. This meant it could be applied to both small objects, such as spheres, to calculate their revolution around larger bodies, as well as to massive objects like planets, and still yield accurate results. However, in the 19th century, astronomers observed a peculiar anomaly in the skies. The planet Uranus was deviating from the orbit predicted by Newton's laws. Instead of following a perfect elliptical path, its orbit wobbled slightly. This raised two possibilities. Either Newton's laws were incomplete, or an undiscovered planet's gravity was influencing Uranus's orbit. And then they found Neptune. These discoveries cemented the validity of Newton's laws. Another scientist, despite having no formal education, went on to discover a fundamental force. His name was Michael Faraday. He demonstrated that moving a magnet inside a loop of wire generates electricity, a groundbreaking observation at a time when the relationship between electricity and magnetism was completely unknown. It was also shown that a moving electric field could create a magnetic field. Over time, Faraday realized that these two phenomena were actually interconnected, like two sides of the same coin. However, due to his lack of formal education, he lacked the mathematical tools to fully describe his discoveries. Instead, he filled notebooks with unusual diagrams depicting lines of force, resembling the patterns formed by iron filings around a magnet. Faraday also introduced the concept of a field, one of the most crucial ideas in physics. A field consists of lines of force spread throughout space. For instance, magnetic lines encircle every magnet, with Earth's magnetic field extending from the North Pole, spreading through space, and returning to the South Pole. Even Newton's theory of gravity can be described in terms of fields, as the Earth moves around the Sun within its gravitational field. Faraday's discovery helped to explain the source of Earth's magnetic field. As the Earth rotates, the electric charges within it also rotate. This continuous movement of charges inside the Earth generates the magnetic field. Newton demonstrated that objects move due to forces, which can be described using calculus. Faraday, on the other hand, showed that electricity moves because it is driven by a field. This led to the need for a new branch of mathematics, which was later formalized by James Clerk Maxwell as vector calculus. Just as Kepler and Galileo laid the groundwork for Newtonian physics, Faraday's work set the stage for Maxwell's equations. Maxwell, a brilliant mathematician, used these equations to summarize the behavior of electricity and magnetism. He established that a moving magnetic field generates an electric field, and vice versa. Maxwell came up with a revolutionary idea. What if a changing electric field created a magnetic field, which in turn generated another electric field, and so on? He realized this interaction would produce a moving wave of alternating electric and magnetic fields. Using vector calculus, Maxwell calculated the speed of this wave to be 310,000. Maxwell's equations exhibit duality, meaning the equations remain unchanged if you swap the electric field with a magnetic field. This symmetry shows that electricity and magnetism are two aspects of the same force, marking a major scientific breakthrough of the 19th century. At that time, scientists believed they had discovered everything, thinking that Newton's laws and Maxwell's equations could explain all natural phenomena. However, around the start of the 20th century, a young scientist had many questions on his mind. He wondered about surpassing a beam of light. That scientist would become one of the greatest minds in history: Albert Einstein. Einstein asked a groundbreaking question: what happens to Maxwell's equations if you travel at the speed of light? No one had considered this before. Using Maxwell's theory, He calculated the speed of light from a moving object like a train. Based on Newtonian mechanics, he expected the light speed to be the sum of its own speed and the train's. Similarly, if you moved alongside the light beam, it should appear stationary. However, this contradicted the laws of physics and led Einstein to challenge conventional ideas about motion and light. To Einstein's surprise, the light beam didn't freeze as expected. Instead, it continued moving at the same speed. This seemed impossible. Newton's laws said you could catch up to anything if you moved fast enough. But Maxwell's equations showed that no matter how fast you traveled, you could never catch up to light. This realization was profound. Either Newton or Maxwell was wrong. He realized that since the speed of light is measured using clocks and meter sticks, and since light speed remains constant no matter how fast you move, space and time themselves must warp to maintain that constant speed. That means if you're on a fast-moving spaceship, the clocks inside the ship run slower than those on Earth. The faster you move, the more time slows down. This is explained by Einstein's special relativity. So, the question "what time is it?" depends on your speed. If the spaceship is moving close to the speed of light and we observe it from Earth, everyone on board would appear to move in slow motion. Things inside the ship would also look squished and heavier. However, for those inside the spaceship, everything would seem completely normal. If you put an atomic clock on an airplane and compare it to one on the ground, the clock on the plane will run slightly slower by a tiny amount, about 1 part in a trillion. Since space and time can change, everything else like matter and energy must also change. The faster you move, the heavier you become. But where does the extra weight come from? Comes from the energy of motion, meaning some of that energy is converted into mass. The exact relationship between matter and energy is given by the equation E=mc². This formula answers a fundamental question in science. Why does the sun shine? The sun shines because, under high temperatures, hydrogen atoms are compressed, and some of their mass is converted into energy. Battle between relativity and quantum mechanics. For more than half a century, even amid some of the greatest scientific achievements in history, physicists have quietly recognized a looming challenge. The issue is this. Modern physics rests on two foundational pillars. One is Albert Einstein's general relativity, which offers a framework for understanding the universe on the largest scales. Stars, galaxies, clusters, and the vast cosmos. The other is quantum mechanics, which explains the universe on the smallest scales, from molecules and atoms down to subatomic particles like electrons and quarks. Despite the remarkable accuracy with which both theories' predictions have been experimentally confirmed, they lead to a troubling conclusion. As currently formulated, general relativity and quantum mechanics cannot both be correct. Physicists focus on either small, light things like atoms or large, heavy objects like stars and galaxies, but not both. This lets them use either quantum mechanics or general relativity and easily ignore the contradictions between the two. But the universe can be extreme. Inside a black hole, huge masses are compressed into tiny sizes. And at the Big Bang, the entire universe emerged from a microscopic point. In these cases, both quantum mechanics and general relativity are needed at the same time because they involve both the very small and the incredibly massive. The first major conflict in physics was identified in the late 1800s. According to Newton's laws, if you move fast enough, you could catch up with a beam of light. However, Maxwell's laws of electromagnetism said this was impossible. Einstein resolved this issue with his theory of special relativity, which transformed our understanding of space and time. Space and time became flexible concepts that changed depending on motion. This led to the second conflict. Einstein's special relativity showed that nothing can travel faster than light, but Newton's theory of gravity implied that gravitational effects move instantly across space. Einstein resolved this too with his general theory of relativity in 1915, which showed that space and time can bend and curve in response to matter and energy, transmitting gravity. Thus, space and time became active participants in the workings of the universe rather than passive, unchanging backdrops. The pattern repeated once more. While general relativity resolved one issue, it led to another. In the early 1900s, physicists developed quantum mechanics to address problems with 19th-century physics at the microscopic level. The third and most profound conflict is between quantum mechanics and general relativity. The smooth, curved space from general relativity clashes with the chaotic, microscopic behavior described by quantum mechanics. Here enters string theory. The theory offers a way to unify all of nature's forces and phenomena, from the smallest particles to the largest galaxies, under a single grand principle. For a long time, physicists believed that protons, neutrons, and electrons were the fundamental building blocks of matter. They were considered indivisible, like tiny, indestructible spheres. However, in 1968, experiments at the Stanford Linear Accelerator Center revealed a surprising truth. Protons and neutrons are not fundamental particles. Instead, they are composed of even smaller particles called quarks. Protons are made up of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up quark. These quarks combine to form the core of atoms, with protons carrying a positive charge and neutrons having no charge. The specific combination of up and down quarks within these particles determines their properties. These up and down quarks, along with electrons, are the building blocks of all the matter we observe on Earth and throughout the cosmos. While there is no experimental evidence to suggest that these particles themselves are further divisible, our understanding of the universe continues to evolve. Evidence for a deeper reality. The discovery of quarks led to a deeper understanding of the universe, but it also raised new questions. Scientists began to uncover evidence for the existence of additional fundamental particles. In the mid-1950s, Frederick Raynes and Clyde Cowan provided conclusive evidence for the existence of neutrinos, elusive particles predicted in the early 1930s by Wolfgang Pauli. Neutrinos are incredibly light and interact very weakly with matter, allowing them to pass through vast distances without being significantly affected. In fact, billions of neutrinos from the Sun are passing through your body every second. Along with neutrinos, scientists discovered the tau, a much heavier cousin of the electron. They also identified 2 new neutrino-like particles, the muon neutrino and the tau neutrino, which join the already known electron neutrino. These particles are created during high-energy collisions and exist only for extremely short periods, meaning they do not contribute significantly to the everyday matter that we encounter. Antimatter and particle families. Each particle also has an associated antiparticle, which has the same mass but opposite properties such as charge. For instance, the antiparticle of the electron is called a positron. It has the same mass as the electron but carries a positive charge instead of the electron's negative charge. Charge. When matter and antimatter come into contact, they annihilate each other, producing pure energy. This annihilation is a key reason why antimatter is extremely scarce in the natural world. Scientists have found that particles can be categorized into 3 distinct groups, often referred to as families. Each family consists of 2 types of quarks, an electron or one of its heavier relatives, and a specific neutrino type. While these particles are similar in properties, their mass increases from one family to the next. By studying matter at incredibly small scales, about a billionth of a meter, researchers have determined that all known matter, whether naturally occurring or created in laboratories, is composed of combinations of particles from these families, along with their antimatter counterparts. This discovery sparked numerous questions. Why do we have so many fundamental particles when most of what we see around us only requires electrons, up quarks and down quarks? Why are there 3 particle families instead of 1, 4, or another number? And what causes their masses to vary so much? For instance, why is the tau particle over 3,500 times heavier than an electron, or the top quark more than 40,000 times heavier than an up quark? Are these numbers just random, deliberate, or could there be a deeper scientific reason behind them? Things get even more complex when we think about the forces in nature. We see countless ways that objects interact with each other. Balls get hit by bats, nuclear bombs can cause massive explosions, we can push, pull, throw, shake or crush objects or change them by freezing, heating or burning them. Over the last 100 years, physicists have found that all these interactions can be traced back to just 4 fundamental forces: gravity, electromagnetism, the weak force, and the strong force. Over the last 100 years, scientists have found that all forces have 2 basic things in common. One is that, at a very small level, each force comes from a specific particle, which is like the smallest piece of that force. For example, when a laser shines light, it's sending out tiny particles called photons, which carry the electromagnetic force. In the same way, the weak and strong nuclear forces are carried by particles called weak gauge bosons and gluons. Gluons help hold the center of atoms together like a glue. By 1984, scientists had proven the existence of these particles. There is also a predicted particle for gravity called the graviton, but it hasn't been found yet. The second shared trait of forces is that just as mass determines how gravity affects a particle and electric charge controls how the electromagnetic force acts on it, particles also have strong charge and weak charge. These charges determine how the strong and weak forces influence them. While scientists have measured these properties very precisely, there's no clear explanation for why the universe contains these specific particles with their particular masses and force charges. Despite their shared features, studying the fundamental forces raises more questions. For example, why are there 4 basic forces and not more or fewer? Why do they behave so differently? Why are the strong and weak forces limited to tiny scales while gravity and electromagnetism work over great distances? And why do these forces vary so much in strength? These aren't just abstract questions. Even small changes in the properties of particles and forces would make the universe completely different. For example, the stable atomic nuclei that make up all the elements depend on a careful balance between the strong force and the electromagnetic force. Protons in the nucleus repel each other because of their electric charge, but the strong force between quarks holds them together. If this balance were off by just a little, atomic nuclei would fall apart. Likewise, if electrons were just a bit heavier, they would combine with protons to form neutrons. This would destroy hydrogen atoms, which are the simplest element, and prevent the formation of more complex elements. The strength of gravity also plays a key role in stars. Gravity pulls matter into the core, fueling nuclear reactions that produce starlight. If gravity were stronger, stars like our Sun would burn out much faster, affecting the possibility of life. If gravity were weaker, matter wouldn't clump together, and stars and galaxies wouldn't form at all. In short, the universe is the way it is because particles and forces have the exact properties they do. But we still don't know why these properties are what they are. Here's where things get exciting. String theory steps in to tackle the mysteries of fundamental particles. Instead of being tiny point-like objects, string theory suggests that if we could look at them with extreme precision, far beyond what we can currently achieve, each particle would actually appear as a tiny one-dimensional loop. Imagine a minuscule vibrating rubber band. This string moves and oscillates, giving rise to the different properties of particles. Physicists, borrowing from the simplest imagery, have called these tiny loops strings. String theory builds on what we already know about particles. In addition to atoms, protons, neutrons, electrons, and quarks, it proposes that the tiniest components are actually tiny vibrating loops called strings. String theory introduces a unified concept that everything at the most fundamental level is made up of vibrating strings. This framework has the potential to explain all forces and matter, offering a comprehensive approach to understanding the universe. It may also provide solutions to the unresolved challenges of general relativity and quantum mechanics. An increasing number of physicists and mathematicians are coming to view it as a promising key to these mysteries. When Einstein was developing his theories, only 2 fundamental forces were recognized: gravity and electromagnetism. Even these forces left him wondering how such seemingly distinct forces could coexist in nature. He rejected the notion that nature was built on such a complex and disconnected design. This led him on a 30-year journey to find what he called a unified field theory, one that he believed would reveal both forces as different expressions of a more profound underlying principle. His pursuit, however, distanced him from mainstream physics, which was focused on exploring the newly emerging field of quantum mechanics. In hindsight, Einstein was ahead of his time. Decades later, the quest for a unified theory has become one of the greatest challenges in modern physics. String theory proposes that the characteristics of particles like mass and charge are linked to the unique ways in which fundamental strings vibrate, similar to how musical notes are produced by vibrating strings on instruments like a violin or piano. In this framework, each particle, such as an electron or a quark, arises from a specific vibration of a string. This concept also applies to the forces in nature. String theory suggests that all matter and forces are ultimately different manifestations of string vibrations, akin to different notes produced by these microscopic strings. Before diving into the concept of strings, it's important to first touch on quantum mechanics, as it is just as essential as the quantum mechanics provides a framework for understanding the microscopic aspects of the universe. Just as relativity alters our perspective for fast-moving or massive objects, quantum mechanics uncovers surprising properties at the atomic and subatomic levels. Einstein's theories of relativity, though revolutionary, lead to logical conclusions once their principles are understood. Quantum mechanics, on the other hand, is different. By 1928, its mathematical framework was set, allowing for incredibly precise predictions. However, most who use quantum mechanics follow its rules without fully grasping why they work. Unlike relativity, it remains difficult for many to deeply understand. Like relativity, quantum mechanics challenges our view of the universe, revealing unexpected behaviors on atomic and subatomic scales. What can we make of this? Does the universe function in such mysterious ways at the microscopic level that the human mind, shaped by everyday experiences, can't fully grasp it? Or could physicists have developed a complicated version of quantum mechanics that obscures the true nature of reality? No one knows for sure. Perhaps in the future, someone will find a clearer explanation, or perhaps not. What we do know is that quantum mechanics shows us that many basic concepts from our everyday world lose meaning at the atomic and subatomic levels, forcing us to rethink both our language and reasoning to understand the universe at these scales. Planck's law explains that the energy of a photon depends on its frequency, and as the wavelength increases, the energy decreases. By using light with lower frequencies or longer wavelengths, we can produce photons with less energy. However, there's a limitation. When waves bounce off an object, the precision of determining the object's position is limited by the wavelength of the wave. In more simpler words, when we use waves to find an object's position, we can only measure its location with an accuracy equal to the wave's wavelength. Think of it like trying to locate a rock beneath the surface of the ocean by observing how waves change as they hit the rock. Before reaching the rock, the waves follow a smooth pattern. But as they pass over the rock, they become distorted. By examining the distortion, you can only estimate the rock's position within a range defined by the wave's length. Similarly, in the case of light, the position of an object can only be determined with an accuracy that's about the same as the wavelength of the light used. In quantum mechanics, there's a trade-off when trying to measure an electron. If you use high-frequency light, which has a short wavelength, you can pinpoint the electron's position more accurately. But high-frequency light has more energy, which can disturb the electron's movement. On the other hand, using low-frequency light, long wavelength, impacts the electron less but makes its position harder to pinpoint. Heisenberg discovered that there's a relationship between how precisely we can measure an electron's position and how precisely we can measure its velocity. If you improve one, you lose accuracy in the other. This isn't just a limitation of the tools used. It's a fundamental principle of nature. Quantum mechanics shows that, at a microscopic level, you can't know both an object's position and velocity with complete accuracy at the same time. The more certain you are of one, the less certain you are of the other. And this principle applies not only to electrons but to all particles in nature. Einstein tried to hold on to classical physics by suggesting that even though quantum mechanics limits what we can know about an electron's position and velocity, the electron still has a definite position and speed just like we used to think. However, in the last few decades, thanks to the work of physicist John Bell and experiments by Alain Aspect and others, we now know that Einstein was wrong. Electrons, and everything else, can't have a specific location and speed at the same time. Quantum mechanics proves that not only can we never measure both exactly, but also that such a claim goes against newer experimental findings. If you trapped a single electron inside a large box and then slowly shrank the box to pinpoint the electron's location, the electron would start moving around more wildly. It's almost like the electron gets anxious as the space gets smaller, bouncing off the walls at unpredictable speeds. Nature doesn't let particles be confined too easily. In a made-up world where quantum effects are more noticeable, even things like ice cubes in a drink would rattle around wildly because of this quantum claustrophobia. Although this is just imagination, in the real microscopic world, particles behave this way. The more you try to confine them to a smaller space, the more erratic their motion becomes. This leads to an interesting phenomenon called quantum tunneling. If you threw a small stone at a thick concrete wall, classical physics tells us it would bounce back since it doesn't have enough energy to break through. But on the level of particles, quantum mechanics says that there's a tiny chance the pellet could actually pass through the wall. This happens because the particles that make up the stone have probability waves, and a small part of those waves can leak through the wall. This possibility, although small, comes from the uncertainty principle in quantum mechanics. In quantum mechanics, there's a trade-off in measurement precision. Heisenberg showed that you can't know both a particle's position and velocity exactly. And the more precisely you measure its energy, the longer the measurement takes. Over short timescales, energy can appear to fluctuate like a particle borrowing energy briefly. This allows phenomena like quantum tunneling, where particles pass through barriers that are impassable in classical physics. While it's unlikely for large objects to tunnel, you'd have to wait longer than the age of the universe for something like walking through a wall. The uncertainty principle is central to quantum mechanics. Things we usually take for granted, like objects having definite positions, speeds, or energies at specific moments, are actually just effects of Planck's constant being very small in our everyday world. When this quantum insight is applied to spacetime, it reveals flaws in gravity's structure, leading to one of the major challenges in physics over the past century. The sole focus of quantum mechanics was on the Schrödinger equation and experiments, but he left out special relativity. He initially tried to include it, but the resulting equation didn't match experimental data on hydrogen. Instead of trying to solve everything at once, he took the approach of addressing one part at a time. He successfully created a mathematical model for wave-particle duality but did not yet incorporate special relativity. In his early work, physicists soon realized that special relativity is essential for a proper quantum framework. The equation E=mc² shows that energy can take many forms, which Schrödinger's approach missed by not including relativity. To fix this, physicists combined special relativity with quantum concepts, focusing first on the electromagnetic force. This led to quantum electrodynamics, a relativistic quantum field theory. It's quantum because it includes uncertainty and probability, and it's a field theory because it integrates quantum ideas into the classical notion of a force field, like Maxwell's electromagnetic field. In a quantum field, think of space filled with invisible field lines made of particles like photons, with energy constantly shifting between fields as they vibrate through space and time. In the Standard Model, just as photons are the smallest units of an electromagnetic field, the strong and weak force fields have their own smallest units. Gluons for the strong force and W and Z bosons for the weak force. These particles are considered elementary, with no internal structure, just like the matter particles in the model. Photons, gluons, and weak bosons transmit their respective forces. For instance, when two electrically charged particles repel each other, it's not just the fields around them doing the work. Instead, the particles exchange photons, similar to how two skaters might push each other by throwing objects back and forth, causing them to move apart. A flaw in the ice skater analogy is that throwing bowling balls always pushes the skaters apart. However, when oppositely charged particles exchange photons, the force is attractive. The photon doesn't directly transmit the force, but rather sends a message on how the particles should respond. For like charges, the messages move apart, and for opposite charges, they come together. This is why photons are called messenger particles for the electromagnetic force. Similarly, gluons are the messenger particles for the strong force, holding quarks together inside protons and neutrons, while weak gauge bosons mediate the weak force, responsible for particle transformations in radioactive decay. Gravity is notably missing from the discussion of quantum forces. Given the success of quantum field theories for the other three forces, one might suggest creating a similar theory for gravity with gravitons as the messenger particles. This idea seems fitting as there are intriguing similarities between gravity and the other forces. The gravitational force ensures that all observers, regardless of their motion, are equal, allowing even those accelerating to claim they are at rest by attributing the force to a gravitational field. This enforces a symmetry of all observational viewpoints. Similarly, the strong, weak, and electromagnetic forces also enforce symmetries, though these are more abstract than gravity's. To understand these subtle symmetry principles, consider this example. Each quark comes in 3 colors: red, green, and blue, which affect how it interacts with a strong force, similar to how electric charge affects electromagnetic interactions. Data shows that interactions between quarks of the same color are identical, as are those between different colors. Even if these colors were shifted or changed, the interactions would remain the same. This type of symmetry, where physics remains unchanged by color charge shifts, is known as strong force or gauge symmetry. String theory suggests that if we could examine the point-like particles of the Standard Model with far greater precision than we currently can, we would discover that each particle is actually a tiny vibrating loop of string. These loops are extremely small, with a typical length around the Planck scale, which is about 10 times smaller than an atomic nucleus. Given how minuscule strings are, it's no surprise that current experiments can't detect them. They are even smaller than subatomic particles. To observe them directly, we'd need a particle accelerator millions of billions of times more powerful than anything we've built so far. Before we dive into the fascinating consequences of replacing point particles with strings, let's first consider a simpler question. What are strings made of? There are 2 possible answers to the question of what strings are made of. First, strings could be truly fundamental, like the atoms of the ancient Greeks, uncuttable and the smallest possible building blocks of the universe. In this view, strings aren't made of anything smaller because that would make them less fundamental. Just as letters are the basic units of written language with no deeper components, strings would be the smallest indivisible elements of the physical world. The second answer acknowledges that we don't yet know if string theory is the final word on the nature of reality. If it's incorrect, then strings may not be fundamental at all. History has shown that with each deeper understanding of the universe, we discover smaller and smaller components. So it's possible that strings are just another layer, potentially made up of even smaller structures. While there are some theoretical hints that strings could have substructure, no definitive evidence exists yet, and further research is needed. For simplicity, let's consider strings as the most fundamental building blocks of particles. The Standard Model of particle physics, which included 2 main components, fermions and bosons, has 2 major shortcomings. It doesn't include gravity, and it can't explain why particles and forces have the specific properties they do. The model relies on experimentally measured values but offers no deeper reason for why these particular particles and forces exist or why the 19 parameters that describe them have their specific values. This makes the properties of the universe feel arbitrary, as if they could have been different by chance. While the Standard Model can predict interactions based on measured data, it can't explain the fundamental properties themselves, as it could easily adjust to different particle configurations if experiments had revealed them. String theory is fundamentally different from other theories. It requires only one key input, a number that sets the scale for measurement, and can explain all properties of the microscopic world. To grasp this, think of familiar strings like those on a violin, which can vibrate in countless patterns, creating different musical notes. Similarly, in string theory, the strings vibrate in specific patterns, with peaks and troughs fitting their length. The key idea is that just as a violin string's vibrations produce different notes, the vibrations of a fundamental string determine a particle's mass and force charges. The connection between a particle's mass and string vibrations is clearer when considering energy. A string's vibrational energy depends on its amplitude, which can be equated to the height of the vibrations, and its wavelength, simply put, the distance between peaks. Larger amplitudes and shorter wavelengths mean more energy, while smaller amplitudes and longer wavelengths mean less energy. This is like a violin string. Plucking it harder results in more intense vibrations, while softer plucking produces gentler ones. According to special relativity, energy and mass are connected. More energy means more mass. So in string theory, Heavier particles have strings with more energetic vibrations, greater amplitude and shorter wavelength, while lighter particles have strings that vibrate less energetically. A particle's mass, which determines how it interacts with gravity, is directly linked to its string's vibration pattern. Physicists have also found that the same is true for other forces. The way a string vibrates determines a particle's electric, weak, and strong charges. This applies not only to matter particles, fermions, but also to force-carrying particles like photons, weak-gauge bosons, and gluons, which are all different vibration patterns of strings. Importantly, one of these patterns corresponds to the graviton, meaning gravity is naturally included in string theory. According to string theory, the properties of elementary particles come from the specific way their internal strings vibrate. This is a major shift from earlier views where each particle was thought to be made of different stuff. For example, electrons had negative charge while neutrinos had none. String theory changes this by suggesting that all particles are made of the same kind of string. The differences between particles are due to the different vibrational patterns of their strings, like different musical notes played on the same instrument. The universe, therefore, is like a cosmic symphony of vibrating strings. Since the forces between these fundamental strings can describe all physical events and processes in the universe, string theory offers the potential for a single, comprehensive description of the physical universe, the theory of everything. String theory requires knowing the tension of its loops, much like how everyday strings like shoelaces or violin strings have different tensions. Since fundamental strings are too tiny to measure directly, scientists use an indirect method. In 1974, 𝐒𝐭𝐫𝐢𝐧𝐠 and Schwartz proposed that one string vibration pattern represents the graviton, a particle responsible for gravity. Their calculations showed that the force of gravity is tied to the string's tension, which turns out to be extremely high, about 1.39 tons per square inch, called the Planck tension. This makes fundamental strings incredibly stiff, much more than familiar strings. Unlike violin or piano strings, fundamental strings in string theory aren't fixed in size. Their large tension makes them shrink to a tiny size, about 10 to the power of -33 cm, which is the Planck length. This tension also gives the strings very high energy because, like tighter strings on instruments, they are harder to vibrate. Strings with more tension hold more energy than those with less tension, even if they vibrate in the same way. The energy of a vibrating string depends on two things: how it vibrates, more complex patterns mean more energy, and the string's tension. Higher tension means more energy. You might think gentler vibrations would lower the energy, but quantum mechanics says energy comes in fixed units, not continuously. The energy is always a whole number multiple of a minimum amount, which depends on the string's tension and how it vibrates, number of peaks and troughs. The key point is that the minimum energy in string theory is linked to the string's tension, which is enormous. As a result, the smallest energy levels are also huge, measured in multiples of the Planck energy. Using Einstein's formula E=mc², this energy translates to a mass about 10 to the power of 19 times that of a proton, known as the Planck Massachusetts. This mass is roughly the same as a grain of dust or a million bacteria. So, in string theory, the typical mass of a vibrating loop is some whole number multiple of the Planck mass, referred to as the Planck scale. This raises an important question related to reproducing particle properties. If string theory's natural energy scale is vastly higher than a proton, how can it explain much lighter particles like electrons, quarks, and photons? The answer lies in quantum mechanics. Due to the uncertainty principle, nothing is ever completely still, and even strings in string theory undergo quantum vibrations. Surprisingly, these quantum jitters can cancel out some of the string's vibrational energy, reducing it by an amount close to the Planck energy. This results in lower energy vibrations that correspond to particles with much smaller masses, like those in particle physics. For instance, 𝐒𝐭𝐫𝐢𝐧𝐠 and Schwartz found that the graviton vibrations cancel out perfectly, resulting in a massless particle, which matches the behavior of the gravitational force. However, most string vibrations correspond to much heavier particles, far greater in mass than a proton. This suggests that the light particles we observe emerge from the complex energy interactions of strings. Even a heavy particle like the top quark, which is 189 times the mass of a proton, can only form if the string's huge Planck scale energy is cancelled out with extreme precision, better than 1 part in a 100 million billion. It's like being given an enormous amount of money and needing to spend all but exactly $189. A nearly impossible challenge. While string theory calculations show that such energy cancellations can happen, verifying them with exact precision is beyond our current understanding. Still, many of the properties of string theory, which are less dependent on these tiny details, can be confidently studied. Additionally, strings can vibrate in countless patterns, raising the question of whether this infinite variety could mean there are infinitely many particles, potentially conflicting with experimental data. And the answer to this question is a big yes. According to string theory, each of the infinite vibrational patterns of strings corresponds to a different particle. However, because of the high string tension, most of these patterns produce extremely heavy particles, far heavier than the Planck Massachusetts. Only a few low-energy patterns correspond to lighter particles. Since our particle accelerators can only reach a fraction of the energy needed to detect these heavy particles, direct searches in labs are currently impossible. However, indirect methods exist, such as studying the early universe. Smear out the interaction across a broader area. Different observers see the interaction happening at various points, effectively spreading the force. In the case of gravity, this smearing softens its intensity at very small scales, replacing problematic infinities with manageable finite results. This smoothing also calms the jitteriness of space at sub-Planck scales. In string theory, sub-Planck scale details that point particle theories would detect are blurred and made harmless, like seeing the world through blurry glasses. If string theory truly describes the universe, there's no way to sharpen these tiny details. The conflict between general relativity and quantum mechanics, which only arises at these incredibly small distances, is avoided because string theory sets a lower limit on how small distances can be. This allows the laws of large and small scales to work together without the problems that would normally occur at ultramicroscopic distances. Strings are unique for two reasons. First, they can be described within quantum mechanics despite being extended objects. Second, one of their vibrational patterns matches the properties of the graviton, meaning gravity is naturally included in their structure. Just as string theory suggests that point particles are only mathematical idealizations, it raises the question: could strings also be idealized as infinitely thin? Might they actually have some thickness like a thin tube or donut? Past attempts by physicists like Heisenberg and Dirac to build a theory with three-dimensional objects have faced major challenges, making this idea difficult to pursue. In the mid-1990s, string theorists unexpectedly discovered that higher-dimensional objects play an important role in string theory. It became clear that string theory doesn't just involve strings. It includes various components of different dimensions, like two-dimensional frisbee-like shapes and three-dimensional blobs among others. These insights, introduced during the second superstring revolution, music. We can be convinced of the existence of additional curled-up spatial dimensions through both theoretical necessity and experimental limitations. Historically, the concept was first proposed by 𝐒𝐭𝐫𝐲𝐧𝐠 and refined by Klein, suggesting that the universe might have dimensions beyond the three we experience. These additional dimensions could be tightly curled up, so small that they escape detection by current instruments. However, the idea of extra dimensions might seem artificial, especially given that we can explore distances smaller than a billionth of a meter. This limitation allows for all kinds of fanciful possibilities, even tiny civilizations of green people. While extra dimensions seem more reasonable, both ideas might seem equally arbitrary since they can't be tested right now. String theory changes this perception. It addresses the main issue in modern physics, the conflict between quantum mechanics and general relativity, while also unifying our understanding of nature's fundamental particles and forces. To achieve this, string theory requires extra spatial dimensions. Quantum mechanics tells us that our predictions are limited to probabilities, which are always between 0 and 1. If calculations yield probabilities outside this range, such as infinite or negative probabilities, it signals a problem with the theory. Initially, string theory seemed to suffer from these issues, but physicists worked hard to identify the cause. The issue arises when a string is restricted to a two-dimensional surface, which limits its vibrational directions to just two. If the string can move off the surface, it gains an additional direction, increasing its vibrational possibilities. In a universe with more spatial dimensions, a string can vibrate in even more directions, which is crucial for string theory's success. Physicists discovered that string theory calculations only work properly if strings can vibrate in 9 spatial directions. Without these 9 dimensions, calculations produce errors like negative probabilities, which don't make sense. The solution comes from an idea by 𝐒𝐭𝐫𝐲 and Klein. In addition to the 3 large spatial dimensions we experience, there could be 6 tiny curled-up dimensions. String theory requires these extra dimensions for consistency, meaning that the universe has a total of 10 dimensions, 9 of space and 1 of time. This concept saved string theory from being dismissed as irrelevant. While it's known that calculations show 9 space dimensions work, there's no simple explanation for it. Physicist Ernest Rutherford noted that if you can't explain something simply, you might not fully understand it. This might apply to the extra dimensions in string theory. Interestingly, in the mid-1990s, new research suggested that string theory actually needs 10 spatial dimensions plus time, totaling 11 dimensions. Why are 3 spatial dimensions large and extended while the others are tiny and curled up? Why aren't they all extended or all curled up or something in between? Currently, we don't have an answer to this question. If string theory is correct, we should eventually find an explanation, but our understanding of the theory isn't advanced enough to do so yet. That's not to say there haven't been attempts. For example, from a cosmological viewpoint, it's been proposed that all dimensions started out curled up and then in a Big Bang-like event, 3 spatial dimensions and 1 time dimension expanded to their current size while the others remained small. Although some rough ideas have been proposed to explain why only 3 spatial dimensions expanded, these are still in the early stages. For now, we assume that only 3 dimensions are extended as that's what we observe. A key goal of current research is to prove that this assumption comes directly from the theory itself. With the need for extra dimensions in string theory, could some of them be additional time dimensions instead of space dimensions? This idea might seem strange. We are used to the concept of multiple space dimensions because we live in a world with 3, but what would it mean to have more than 1 time dimension? Would one behave like the time we experience while the other works differently? It gets even weirder if we imagine a curled-up time dimension. For example, if an ant walks around a curled-up space dimension, it will eventually return to the same spot. This makes sense because we can return to the same place in space. However, if time were curled up, moving through it could mean returning to a previous moment in time, which is something we never experience. Time as we know it only moves forward, and we can't go back. While it's possible that extra time dimensions work differently from the familiar one we know, this would drastically change our understanding of time. Some scientists are investigating the idea of extra time dimensions in string theory, but there's no clear answer yet. For now, in string theory, we'll stick with the idea that all the extra dimensions are spatial, though the idea of new time dimensions could be explored in the future. Years of research have shown that even though we can't directly see any extra dimensions because they're too small, they still have significant effects on the physics we observe in string theory. This connection is particularly clear. The masses and charges of particles in string theory are determined by the ways the strings can vibrate. Imagine a tiny string vibrating, and you'll see that its vibrational patterns depend on its surroundings. For example, ocean waves in the open sea can move freely in different directions, just like a string in large open dimensions. But when waves pass through a narrow area like a canal, their movement is affected by things like water depth and the shape of rocks. Similarly, musical instruments like an organ pipe or a French horn produce specific sounds because of how air vibrates inside them, determined by the instrument size and shape. In the same way, extra curled-up dimensions influence how strings vibrate. Since strings vibrate through all the dimensions, the way these extra dimensions are twisted and curled affects the possible vibration patterns. These patterns, shaped by the geometry of the extra dimensions, determine properties like particle masses and charges that we observe in our familiar three-dimensional space. This point is so important that it's worth emphasizing again. In string theory, the universe is made up of tiny strings, and the way these strings vibrate at a microscopic level determines the masses and charges of particles. String theory also says there are extra dimensions of space that are curled up so small we can't see them. However, tiny strings can move through these small spaces, and as they do, the shape and size of these extra dimensions affect how the strings vibrate. Since the vibrations determine particle properties like mass and charge, it means the basic features of the universe depend heavily on the geometry of these hidden dimensions. Understanding the shape and nature of these curled-up dimensions is a key goal in string theory research. The extra spatial dimensions in string theory can't be shaped just anyway. The theory's equations place strict limits on how they can be arranged. A specific type of six-dimensional shape known as 𝐒𝐭𝐫𝐢𝐧𝐠 spaces fits these requirements. These shapes were studied before string theory and play a key role in understanding how these extra dimensions work. Although the math behind 𝐒𝐭𝐫𝐢𝐧𝐠 spaces is complex, we can get a rough idea of what they look like through visual representation. Keep in mind, though, that trying to show a six-dimensional shape on a two-dimensional surface causes distortions. There are many different 𝐒𝐭𝐫𝐢𝐧𝐠 shapes, but they are still rare compared to the infinite number of possible shapes. To sum it up, imagine replacing the two curled-up dimensions with a 𝐒𝐭𝐫𝐢𝐧𝐠 space. This means that at every point in our familiar three dimensions, there are six extra dimensions that are tightly curled into complex shapes. These extra dimensions are everywhere. For example, when you move your hand in a big arc, you're not just moving through the three familiar dimensions but also through these tiny curled-up dimensions. Because these dimensions are so small, you pass through them countless times without even noticing. So when you move your hand, you don't really sense the tiny journey through these extra dimensions. There are some criticisms of string theory. Critics argue that the theory is all talk, that beauty alone isn't a reliable guide in physics, that it predicts too many universes, and most importantly, that it can't be tested. A famous astronomer named Kepler was once misled by the appeal of beauty in science. He was fascinated by the idea that the solar system looked like a series of regular shapes stacked inside one another, similar to Russian dolls. This idea, which was based on ancient Greek shapes like cubes and pyramids, seemed beautiful but turned out to be completely incorrect. Recently, some physicists have criticized string theory, arguing that beauty alone isn't a good guide for finding the truth in physics. Just because string theory has elegant math doesn't mean it's correct. They point out that many beautiful theories have turned out to be dead ends. Paul Dirac, a famous physicist, also believed in this idea. He thought that striving for mathematical beauty was key in developing theories and even discovered his well-known theory of the electron by working with pure math rather than experimental data. However, beauty in physics can sometimes be misleading. Physicist Sabine Hossenfelder has noted that many beautiful theories about unified forces, new particles, and other ideas have been proven wrong. So relying on beauty alone isn't a reliable method. The biggest criticism of string theory is that it's untestable. The energy needed to test it is so high that it's far beyond anything we can currently achieve. For example, the energy of gravitons according to string theory is a quadrillion times greater than what the Large Hadron Collider (LHC) can produce. Building an LHC that's a quadrillion times larger would be like needing a particle accelerator the size of a galaxy. Additionally, each solution in string theory describes an entire universe, and there might be an infinite number of these universes. Testing the theory directly would require creating new universes in a lab, something far beyond our current capabilities. So string theory seems hard to test directly. However, supporters aren't discouraged. They argue that most science involves indirect evidence, like studying light from the sun or remnants of the Big Bang. Similarly, we might find indirect evidence for string theory through things like dark matter. For example, astronomers recently discovered that only about 5% of the universe is made up of ordinary atoms. The rest is dark matter and dark energy. Dark matter, which makes up about 27% of the universe, is invisible but affects the movement of galaxies. One dark energy, which makes up about 68% of the universe, is even more mysterious and causes galaxies to move apart. Some believe that clues about string theory might be hidden in these unseen parts.